Okay, today we're going to do a derivation of the law of cosines. The law of cosines is a tool that we can use to basically solve any triangle, find all of the angles, and find all of the sides of a triangle. And the triangle does not have to be right. And that's very important because in the past we've been able to look at any right triangle, and if we know basically just two pieces of information about it, we can solve the entire triangle. For instance, if we know this side A and this side B, you can then find the hypotenuse and you can find the angles using inverse trig functions. For instance, this angle would be the inverse tangent of B over A. And that one would be the inverse tangent of A over B. Pythagorean theorem to find the missing side. And of course, if you're given the angle and one side, so this was angle theta, and one side, that's sufficient to figure out all the other pieces of the triangle. One thing you're not able to determine is if you're given these two angles, you actually don't know whether the size of this triangle. This triangle could be as big or as small as you want it to be. Okay, so that's all well and good. We can find right triangles, but there's plenty of triangles out there that are not right. In fact, the vast majority aren't right. So how would you find the missing sides and missing angles of those triangles? Well, the law of cosines is what's going to do it for us. So first I will draw a picture to help us labeling sides and stuff of this triangle, and write down what the law of cosines is for the triangle we've drawn. So if we have a triangle ABC like this, and traditionally you're going to label the side opposite the angle lowercase. So if the side is opposite A, you'll label this side lowercase a. Side opposite B is lowercase b. Side opposite C is lowercase c, so forth. Okay, so the law of cosines says then that if you know two sides and the angle inscribed between them, for instance, if I know the measure of this side B, the measure of this side C, how long those sides are, and I know the angle A, then I can figure out what this side is, what the third side is. So the law of cosines says that a squared equals b squared plus c squared minus 2bc times the cosine of a. So what this should look familiar to you, what should look familiar is this a squared equals b squared plus c squared. Well, usually these are a and b and that's c, but it's basically this is the Pythagorean theorem part. Pythagorean. It looks a lot like the Pythagorean theorem, and this is like the correction. Because not all triangles are right. So one thing to note, if angle A is in fact a right angle, then this is the Pythagorean theorem. So if measure of angle A is 90 degrees, then we have a squared, which would be the hypotenuse. This would be A. This is A, the hypotenuse. A squared equals b squared plus c squared. Minus 2bc cosine A. You write that over here. So a squared equals b squared plus c squared minus 2bc cosine of 90 degrees. And the cosine of 90 degrees, as we recall from the unit circle, is equal to 0. And so this correction term, this part, is 0. And it's just the Pythagorean theorem. That's good. Okay, well, how do we get this identity? I'm going to draw some pictures or some triangles into this triangle to try to show that this is actually true. A squared is equal to b squared plus c squared minus 2bc cosine a. So the first step is to draw in a perpendicular segment, basically the altitude of the triangle from B down to side AC. So what we did was we broke up this side into two segments, and I can give them names, X and Y. And remember, I'm under the impression that I know what this angle is. I know how large the angle A is. So what can I say about X? Well, I know this, that the cosine of A is X divided by C, because this is a right triangle now. The cosine of A is the adjacent side, X divided by C, the hypotenuse. So I can solve this for X then and get C times cosine A equals X. So why don't I replace this with C times the cosine of A. So that side is C cosine A. This side would be C sine A. And I'll just justify that a little bit. We can call this thing H if you want. And you know that the sine of A equals H over C. Therefore, solving for H, C sine A equals the height of this triangle. So this is C times sine A. Okay. So if I want to get what the length of this side is, I can use the Pythagorean theorem on this triangle over here. Okay, so let me erase this part. So we know that a squared equals this length y squared plus the height squared, c squared sine squared a. Or maybe I should just, I'll write it out. C sine a quantity squared, which at this point we know that this is c squared sine squared. But I want to try to get this to look like this. So I'm going to replace y, which is this length, with something that involves b and this side. So I can see that y and c cosine a, if I add them together, is going to give me this entire side. So that says that b equals y plus c times the cosine of a. And so that means that y is just, well, subtracting c cosine a from both sides. Cosine a. B minus c cosine a equals y. So I can take this and replace y, make a substitution. It says that y equals b minus c cosine a. So what do we get when we do that? We're going to get a squared equals b minus c cosine a squared, all in parentheses. Remember, whenever you make a substitution, use parentheses so that you don't forget that it's this entire, this difference is being squared. Plus c squared sine squared a. Well, we're close. We're very close. This expression has no sine squareds in it, but I see a cosine a. So how might I get from here up to this statement? Well, I want to get rid of these parentheses. So we should remove them by squaring this difference. So we're going to FOIL b minus c cosine A times itself, b minus c cosine A times b minus c cosine A. So that means we're going to get b times b. Don't forget about this term over here, c squared sine squared A. So you get b times b is b squared. B times negative c cosine A is minus bc cosine A. And then another minus bc cosine A, so that is two of them. And then negative c cosine A is plus c squared cos squared A. And if you know what's going to happen, right here we have c squared cos squared A plus c squared sine squared A. So right here we can factor c squared out. And note that this is just 1. So we get c squared from this piece right here, which ultimately gives me, right, take this up to the top, b squared plus c squared minus 2bc cosine A. And that's all equal to a squared. So the key in this proof was making the triangles, was finding right triangles within this non-right triangle, and then getting these sides in terms of the angle A and the sides C and B. But and note, one thing that's very important is that this statement here does not depend on these letters really. It's just that you know B and C and the angle between them. So you know two sides and the angle between them. So there's an analogous statement to this if you know angle C or you know angle B. So the one that is for angle C would be c squared equals a squared plus b squared minus 2ab cosine C. And then if you know angle B and these sides, you would have b squared equals a squared plus c squared minus 2ac cosine B. So these are all saying the same thing as this one. It doesn't depend, all that matters is that you know two sides and the angle between them, which is SAS.